Hello everyone, welcome back to this elementary of stereology for quantitative metallography course. And so far you have seen the lectures given by Professor Sangal. I was also showing some demonstrations about calculation of all these stereological parameters on some of the nodular cast iron microstructure. So, in this tutorial what I am going to do is I am going to continue the calculation what I have demonstrated in the lecture itself. So, some of the aspects which I felt that what I showed in the form of Excel sheet was little fast, and then I thought let me come back and then work it out in a much slow manner so that you can appreciate them in a better way. So, what I am going to do today is just going to continue that exercise. What did we do the other day? We took the cast iron, nodular cast iron microstructures. In fact, that was performed inside the class. Almost all the students performed the events of point counting to calculate the point fraction, and then we just entered all the data into the Excel sheet, and then we continued to use that data as and when the lecture progresses and for demonstration of new stereological parameters as we progresses. So, this is what we have been doing. So, today what I will do is, if you recall what we have done, the point fraction PP and PL are represented by 95% confidence interval. So, what I am going to do is we are going to format the data whatever we have got. So, if you look back that Excel sheet, we have about 42 data points or 42 events, a small n, and then we collected number of point intersecting these nodular cast iron and microstructure, and also we calculated the PL. So, if you look at this 95% confidence interval, there are two possibilities. We can use either students T distribution or a normal distribution. So, if you recall the classroom, I mean the exercise what we have performed, where we have showed two kind of a table. So, one is a T table and another is a Z table, where you choose the number of degrees of freedom and then take the value of Z or T. So, if you recall, for the 95% confidence level, the T is correspond to 2.021, and for Z it is 1.9599. This is Z distribution or normal distribution. If you recall this formula, what is that? this is x bar minus z s upon root small n, and then x bar plus z s upon square root of n. So, for a PP, if you recall what we have collected from the, what I will do is I will just go back to this Excel sheet and come back. If you look at this PP, what we have got as an average PP 0.17 and then average PL is 0.01, right. So, we are going to use this data again, and then we have also calculated the standard deviation for PP, and we will use this data again for this calculation. So, if you go back and if you substitute all these values, so for PP, what is that you want to get? You will be getting, we have already calculated in the Excel sheet, this is 0.19. So, this is the interval, and for a T distribution we calculate so again we will write so in fact you can, the average PP is 0.17 minus 2.021 into 0.07, that is the standard deviation, square root of 42, and in this case 0.17 plus 2.021 into 0.07 square root of 42. So, here also you can write like that. I have directly put the answers because it is worked out in the Excel sheet. So, we got that value. So, I have just simply taken these two interval values, the lower limit and then higher limit, and this Z distribution, this is what we will get. So, the value would be 0.14 in fact, and then and here it is 0.19. So, if you look at this values for a T distribution as well as the Z distribution, there is no difference here. That is what you have to appreciate. But in general, the T distribution, student T distribution is preferred for where the n is small in general. That is what it is, you have to appreciate. So, you see that both the values are same, whether you use Z distribution or T distribution, the 95% confidence interval for arriving at PP is within 0.14 to 0.19. So, now what we can do is we can go back to this Excel sheet where I have shown we have also computed this D, this average diameter D, and for each case we have calculated this D for all 42 events, you can see that. So, now we can perform a similar exercise. We have already computed this average D and standard deviation and so on. So, this data is here. So, let us complete this confidence interval exercise for D as well. So, you write for T distribution, so you can write 87.660 into 2.021 into 47.32, which is the standard deviation, divided by square root of n, which is nothing but here 42, and there is an error here. So, this is supposed to be a minus sign, and here 87.60 plus 2.021 into 47.32 square root of 42. So, you will get the interval of 72.84, and this is 102.35. So, you can calculate the same thing for the Z distribution also. So, which I think we have already reported in the if not we can leave it there. So, similar way we can report this 95% confidence interval for calculating the mean average mean diameter of the non-dual graphite in the microstructures. So, the other important point I want to mention is we also talk about the relative error. We wrote, if you look at the class lecture lecture, it is like we have Professor Sandeep has proved that the relative error for a point count could be 1 upon square root of n. So, if you see that here we have, which is 0.154 approximately 15% error. So, whatever the calculation we have done for the point fraction, which is equivalent to the volume fraction, if you say that volume fraction of the graphite nodules in this microstructure is about 17%, then it will, you should expect that it is with approximately about 15% of an error. So, you recall that if you want to eliminate much more error in this estimation, then as demonstrated in the lecture, you have to count more. For example, if you want to have the error within 5%, then you have to count more than 3000 particles in the microstructures. So, I have just shown how the data format is finally appears. So, the data appears with the 95% confidence interval range plus with some error estimations. But normally this error estimation is given to check whether the methodology is correct or not. For example, the grid size you have chosen, the particle size you have chosen, whether is there any change, do you need to change this or not. So, in this case what you can now be confident about is within 15, it comes within 15%. So, you can be rest assured that the methodology you have adopted is good, it holds good. So, that is the way I want to show. And the next parameter what we can derive using this PP and PL is the total the total boundary length per unit area, that is BA, which is, you can write in the units micrometer by per micrometer square, which is very important. Unless you write these units, you will not appreciate the meaning of these numbers significantly. So, you have to, this is boundary length is represented in a micrograph by micrometer, and which is, this is per area. So, ratio of two quantities. So, from the relation we know that the average BA can be given by pi by 2 times the average PL. So, we have estimated PL already. So, this PL you can just substitute like this. So, 3.14 divided by 2 into 0.01, that is what we have calculated as an average PL, which comes out to be 0.0157. So, of course, you can also represent this data because it is taken again over all the 42 events of measurements, and then you can represent this similar to what we are representing with the 95 confidence level with 15% of relative error. So, since they are all coming from the similar event, so that holds good here also. See, the other parameter what we are planning to use or estimate using this PP and PL is surface area per unit volume. This is SV. So, you say that here it is micrometer square by micrometer cube. So, surface area per unit volume. So, you can recall this, the relation 2 PL. In fact, there are two relations available. So, one is this. So, we will try to calculate this 0.01, which is equal to 0.02. So, this is the surface area per unit volume for this microstructure, and of course, the same if you use the other formula like SV is equal to 4 by pi BA. So, that also you can see that previously you have done that. What you have done, you can see that this is the BA we have given. So, you use this and then see it will be of same value. So, you will get again, if you 4 by 3.14 into what is that value you have got? It is 0.157. So, 0.0157 which is again so this is what you will get for the so you can verify this. Okay. So, again if you want to represent this SV by 95 confidence interval, you can do that, and of course, the error estimate also will holds good here. So, now the other application of this measurements like using PP and PL, the other important measurement is what we have done is the mean intercept length. That is L bar micrometer. Okay. So, if you recall this formulae, this is 2 pp by PL. So, what we can do is, suppose if I take the first measurement what we have done in the class last time, the PP first value is 0.1389, that is a PP of the first event, and this is the PL 0.0097, which is equal to 28.57 is the average. So, if I go back to this Excel sheet, what I am going to show, so if you see that this is what I have taken, this and these two I have taken, and this is the value I have shown in the calculation. Suppose if I in an Excel sheet, you can simply paste this formula for all this 42 events of measurements. So, you get this, and the average mean intercept length is about 68.80 and the standard deviation is around 37.16. So, what we can now do is, we will again do the exercise of let us write the average mean intercept length. As per the Excel sheet, it is 68.80 micrometer, and we would like to represent L bar at 95% confidence interval. So, we will follow this normal distribution here. So, we know that equation, which is, just to recall, this is the lower limit and this will be the higher limit. If you substitute this, you will get you can write 68.80 minus 1.96 into the standard deviation is 37.16 upon 42, and the other limit is 68.80 plus 1.96 into 37.16 divided by square root of 42. So, you get two values similar to the earlier cases. So, you have 57.56 to 80.03 micrometer. So, this is a range of L bar. What we can calculate is 57.56 to 80.03. So, what is the meaning of this? So, 95% of the particles, the graphite nodular particles in the microstructure will fall within this range. That is the meaning of this 95% confidence level for the if you use the normal distribution. Okay. So, then next thing which I want to just do is we can do the similar exercise for the D. The average diameter of the circular particles, particle D, which is also in a micrometer. In this case, it is in micrometer. So, what are the formulas? The D bar, which is equal to 4 by pi L bar, or I think D is also can be written as 8 by pi into Pp by Pl. So, we can do one calculations. For example, you take one first reading from the Excel sheet. The first reading is 0.1389 divided by 0.0097. So, you get around 36.38 as the average diameter, and I will go back to this Excel sheet. This is for just one event we have done, and if you so this column is populated with the D for each of this event. So, you have Pp, and this is a point count Pp, and you have this PL, and this is intersections, you know that, and we are populating this column with the D, and we have also estimated this average D and the standard deviation for this D. So, we can now again put them in the form of confidence interval. That means D at 95% confidence interval using the normal distribution. Let us again use this. This is for lower limit and this is for higher limit. So, the average D is 86.60 minus 1.96 is as per the normal distribution. The standard deviation is 47.32 divided by square root of 42. The other limit is 87.60 plus 1.96 into 47.32 divided by square root of 42. So, you get again two values. the range of, this will work out to be 73.28 to this one will be 101.91 micrometer. So, this is the average diameter of the nodular cast iron microstructure, the graphite nodules. Okay. So, we have estimated L bar as well as D as well as volume fraction. So, all these things we were able to calculate simply by estimating the point count. So, in this exercises we have not only calculated all these 4 parameters so simply, we have also shown that it is more efficient as per the theory what been taught in the course, and this point count is very effective, and you can derive so many other related parameters also in this case. So, what I will do in the next class, I will take the polycrystalline microstructure which will have a completely space filled grains. So, we will again go through this exercise of calculating the grain size or the mean intercept length, and then how the other quantities like derived quantities we can estimate in the next class. With this I will close this tutorial. Thank you.